Hello all, welcome to this particular course which is designed for computational science in engineering. And just to give you an idea about this particular course, we will just talk about what is preliminary planned for this course and what about. So, myself is Ashok De, who is currently working as associate professor in the Department of Aerospace Engineering at IIT Kanpur. So, I will be the instructor for this course. And what is computer science and engineering? Essentially, this is an evolving field which actually exploits the power of computational tool or computational methodologies to solve or to address issues in practical problems, whether it is in engineering or social sciences or such kind of field. So, the whole idea or the primary idea is that to use the computational techniques or the methodologies to solve the problems. So, in a nutshell or essentially this should talk about or try to frame a framework of framework for solution methodologies for large scale problems. And now, when you use the power of computation, obviously it is based on certain primary things, and like linear algebra or differential equations. So, these are sort of the building blocks towards those devising those kind of methodologies. So, what we are going to cover in this particular course that you can see here. So, as I said, the primary focus actually lies on developing the problem solving methodologies or robust tool for numerical simulation. And here the idea or the goal is to present the fundamental of numerical techniques or scientific computing, and with short codes wherever it is required to sort of establish the key concept. So, obviously, it includes some frameworks of the applied mathematics such as linear algebra, what we see here, then differential equations whether ODE or PDE. So, these are the sort of building blocks which will allow to look at this computing methodologies and then to solve a problem or address the scientific or engineering problem. So, that essentially it would lead to some sort of an skill set which will develop for mathematical modeling based on computational technique. So, as you see that initial part we will be talking about like some of these applied mathematics or algebra, which will include linear algebra, and where we will talk about all these different vectors, vector space, eigenvalues, orthogonality, single value decompositions and all such things. Then talk about little bit or ODEs and then PDEs. But then we will move to this part where we will be talking about all these numerical methods. And as you see that we will talk about in details about solution of the linear system and different issues related to that here when we will come to here, and then ODEs. And one may immediately think about there is nothing mentioned about PDE, we will just talk about a little bit, but not too much, because when you talk about or devise some techniques for PDEs, these actually lead to a typical some of the dedicated course which are in terms of computational fluid dynamics, CFD or computational fluid mechanics, whatever it is. So, that is what we will not go into the detailed discussion of any formulations for PDEs. And these are some of the suggested books which would be kind of useful, like the linear algebra part is pretty much one can follow the Gilbert-Strang or any engineering mathematics book. Then these are the for differential equations, and then there are a couple of numerical techniques books or scientific computing books, and then some computational fluid mechanics books which will talk about discretization and all this. So, that is what pretty much what you can expect that what we will be talking about in this particular course. So, let us start with the discussion, and first thing that as we mentioned that we will start with the linear algebra. So, what linear algebra does that it actually deals. So, one can say linear algebra it deals with linear system. Okay. So, which is not essentially a linear equation, and its behavior or characteristics which may include nature of solution, existence of solutions, and possible ways to obtain the solution. Okay. So, that is what linear algebra does. So, what if you look at that, if my linear algebra, if you talk about, so this will deal with some linear system. So, let us say behavior of that, and then one can look at the uniqueness of solution, or other way one can look at the existence of the solution. So, which will lead to like nature of solution and obviously then how to obtain solution. So, how you deal with the things? So, essentially what you have is that you have a physical system. So, that means there are certain quantities or variables which are associated with that, which will lead to some sort of an governing equations which are kind of going to represent that problem. So, here now simplification of governing equations into linear system for obtaining the. So, basically one can think about the simplification of governing equation into linear system for obtaining solution easily. So, what we will look at it, that we will look at different things like row picture, column picture, matrix form. So, these are the things which will come on the way. Now, let us start the discussion with an simple example. So, let us take an example. So, let us say a system is 2x minus y 0, x plus 2y equals to 0. So, now if we convert that to a linear system, so the linear system of this one can write like 2 minus 1 minus 1 2, this is x and y, which is this is 3. So, this would be 0 3. So, if we change that, then we can write in that way. Now, what we can look at first is the row picture as we mentioned. So, how do we look at it? So, that means we are going by this is the row. So, we will go as a row picture. So, let us draw this 2, 3. And so, when we do that, what it happens that this is 2 minus 1, and so this should be going through 3, and then so like this guy will pass through. So, this is minus x plus 2 y equals to 3. So, this is what it goes through, then the other guy goes through from here, which would be so through this line, which is 2x minus y equals to 0. So, this would be 1 2. So, we will go by the, that means this is first row, this is second row. So, this is how it looks like. Now, if you on the other hand look at the column picture. So, column picture we can rewrite this guy as x into 2 minus 1 plus y minus 1 2, which is 0 3. So, from column picture it says that from some linear combination of two left hand side columns will give the columns of the right hand side. So, what it is that C 1 plus 2 C 2 would be 0 3, again minus C 1 plus 2 C 2 would be minus 4 5. So, you can see this is C 1. So, this guy is C 1, this is C 2. So, if it is C 1 plus 2 C 2, so that gives me 0 3, and if I take in a different combination. So, these are the column vectors which are going to do like this. So, when I plot this guy in a column picture, so this would be interesting to see, like when we do that, so the first column is 2 minus 1. So, this is 2 minus 1. So, this is my 2 minus 1 or sort of C 1, or this is the vector of C 1, and the second one is minus 1 2. So, this is C 2. So, this is C 2. So, minus 1 2, that C 2. Now, what it says C 1 plus 2 C 2 0 3. So, that means comes here. So, this is C 1 and then 2 C 2 if we go, that means we will go parallel to this like this, and then we go another C 2. So, this is C 2, this is C 2. So, we come here 0 3. So, that means when we add this column vector, this is C 1 then 2 C 2 along this direction, that gives me 0 3. Similarly, when we do this guy minus C 1 and then 2 C 2, so this is minus 4 5. So, 1 2 3 4, it should be here. So, C2, so it goes like another C2, then minus C1, so it goes like that. So, this is minus C1, this is C2, so this is minus 4 5. So, this is how the column picture actually behaves. So, the column picture thus basically deals with the linear combinations. For 2D case, the solution was available through both row and column picture, but when you go to 3D, so the things become bit complicated. So, let us take an example on 3D. So, let us say we consider 2x minus y 0 minus x plus 2y minus z minus 1, 3y plus 4z 4. So, now if we write this, this should be written as 2 minus 1 0 minus 1 2 minus 1 0 minus 3 4, this is x y z 0 minus 1 4. So, essentially one can think about this is A, this is x, this is b. So, that gives me A x equals to b. Now, here the row picture, if we see the row picture, so each of the 3 equation denotes 3 planes. So, these are planes. So, each row is 3 planes, and if the solution exists, it will be the point of intersection of 3 plane. So, that means, so the solution if exists will be the point of intersection of 3 planes. Thus, however, it is hard to visualize. So, this is in 3 dimensions, so it would be hard to visualize. Hence, row picture is not an appropriate solution. Essentially, that is what it is, that row picture is not an appropriate for solution if number of unknowns increase or row increases. So, this is not an sort of an easiest way to look at things. So, rather we would try to look at from the column picture. Now, what column picture tells us that this guy can be written as x 2 minus 1 0 plus y minus 1 2 minus 3 plus z 0 minus 1 4, which is 0 minus 1 4. Okay. So, here again if someone at least in 3 dimension draw it. So, this is x, y, z. So, this would be essentially your somewhere 2. So, somewhere C1, somewhere this would be C2 would be somewhere here, like this. Now, another important thing is that these column vectors are not parallel and also they are not arranged as one as the sum of the other two. So, hence these guys, these and these, they are sort of independent vectors. Okay. They are also important to look at, they are also not in the same plane. Here the solution will be, the final solution would be 0 0 1. Now, this kind of graphic visualizations become impractical for more than 3 dimension, because that is where you cannot visualize, but the unknowns, if they are more than 3 or it increases, then even the column picture or the visualization, graphical visualization become difficult. So, the point here is that we have to come up with other ways to find out. So, now the point, if A x equals to b, if the solution, now if solution exists for possible b's, so this system A x equal to b will provide a solution, or the solution exists for possible b's only if all column vectors are linearly independent, and also these vectors will span throughout the space. Now, the B column vector produce 3 different planes in a 3D space, and hence have solution for any B. However, if number of plane produced is less than the space dimension, then the solution may exist only for specific B's. So, that is a very important thing to note. Now, we will look at how we do. So, the Gauss elimination, what it does. In the Gauss elimination, so this would be also associated with back substitution, elementary matrices. So, these are sort of associated with back substitution, elementary matrix, etc. Now, again here also we will try to look at the things through example. Again we will take an example, the 2 3x plus 8y plus z equals to 12, 4y plus z equals to 2. So, if we write them down, 1 3 0, 2 8 4, 1 1 1, which is x y z, 2 12 2. So, this is here is A, this is x, this is B. Now, here in the Gauss elimination process we will do, or it is done by row elimination. So, what we will do here, we will do R 2 is R 2 minus 3 R 1. So, that will give us 1 2 1, 0 2 minus 2. So, 0 4 1, x y z 2 6 2. Now, the second stage what we will do, R 3 is R 3 minus 2 R 2, then we get 1 2 1, 0 2 minus 2 0 0 5. So, this would be x y z. We have 2 6 minus 10. So, here what we get here, this if you look at, you have the diagonal element sitting here, because this is a 3 by 3 matrix, and the below diagonal elements are missing or kind of eliminated. So, this is an upper triangular matrix, and what we get, the solution is received by the back substitution. Now, the point is that if the first pivot, so this is the first pivot, if the first pivot is 0, then rows are exchanged. Gauss elimination fails to give solution when all pivots are 0. So, this is one of the limitations that one has to keep in mind, that if that happens, then no one would be able to. Now, after row operations, what we get? We get an upper triangular matrix U x equals to, let us say, C. So, this what we get, this is a new vector C. So, U is upper triangular matrix. Here what we get, that this will, now the row vectors multiplied with a matrix will give a row vector. For example, we do like, for example, 1 2 5, if we multiply it with the matrix that we have 1 2 1 3 8 1 0 4 1. So, this will give us 1 into 1 3 0, 2 into 2 8 4, 5 is 1 1 1. So, similarly this would be, so when we do that, this gives us 7 38 8. So, this is what we are going to get it 1 4. Now, we come to the elementary matrix. What is that? Now, we have this A, which is 1 2 1 3 8 1 0 4 1. So, here after row operation we got 1 2 1 0 2 minus 2 0 4 1. So, this is what we got after the first row operation that we did. So, this could be multiplied with like, then what we can say, this is my original system 1 2 1 3 8 1 0 4 1, which got into this 1 2 1 0 2 minus 2 0 4 1. So, here is the matrix which got multiplied, and this is called the elementary matrix of E 2 1. So, what is that? We have done R 2 minus 3 R 1. So, here this would be 0. So, minus 3 R 1. So, this is minus 3 1 0, rest would be 0 0 0. So, this is what it does, the elementary matrix. Okay. when we do that, this row operation will, so this should be 1. So, you get back these things. So, we will see that when you have this row operation, instead of doing that, you can have a elementary matrix which is multiplied with this original matrix and get the other one. So, we will continue this discussion in the next session.